Welcome back, everybody. Well, this is what appears to a lot of people to be the hardest problem, and it is kind of long, but it's long only in that it's a little tedious. But it really isn't that hard at all. This is the last of our problem set that's due before the test. This is number 6 on chapter 10, homework number 5, question number 6. So the only thing that's really complicated about this, well, I shouldn't say that, but the only thing that might throw a wrench into your works immediately is the fact that we've got 3 objects and we've got 2 collisions. We've got object 1 right here. I'll call it. In fact, switch layers here. I'll call this object 1. Be better than that. Object 1. Object 2. And object 3, okay? And only one is moving. So this guy is moving. It is looking to crash into object 2, which in turn will then move to crash into object 3. So probably the best way to set this up is simply to make this into 2 problems. Not 2 problems, make it into 2 different collisions. Okay, so what I'm going to do is I'm going to draw a dotted line right down the middle right here. Okay, we're going to have collision. I'm going to label this collision of 1 to 2. And I'm going to call this collision of 2 to 3. And we're going to deal with each one separately, because they're separate events. They're all in one problem, but they're separate events. And now the good thing about this is the fact that, like I said before, only this first mass right here has any initial velocity. Why is that good? That's good because in this first collision, that means the other object right here has no velocity. It's at rest, which is stated right here. So that means we can use a shorter version of our kinetic energy and momentum equations for collision 1 to 2. And the same thing is true over here. Even though this object is going to be, this cart is going to be sliding into 2 is going to be sliding into 3. 3 is also at rest. So that is going to be the second object which is at rest, which allows us to use the shorter equations. So we're not using the long equations at all, only the short ones. But we're going to be doing it 2 times, 1 for each collision. Okay? So let's write down what we know. Well, again, we're not given any numbers here. We're simply given kind of variables. We're told that the mass of cart 1 is 4m, mass of cart 2 is 2m, mass of cart 3 is simply m. All right? So it's like saying m1 equals that, m2 equals that, and m3 equals that right there. Again, some of you who like plugging numbers in right away, you might be a little bit frustrated, but just bear with us here. You can manipulate 4m, 2m, and m just as well as you could manipulate 4, 2, or 1. Okay? And we're also told that the largest cart 1, has an initial speed of VO. So initial velocity of object 1 is VO. Very similar to, come on now, very similar to, if you recall, question 5. It had a similar initial velocity VO. Okay, well, let's break this into 2 separate collisions. And this is, by the way, it's going to probably most likely be a multi-part video, simply because we've got parts A, B, and C right here. This video is going to focus predominantly on simply solving for A, finding the speed of each cart. And then I'll do a separate one for B and for C. Okay, so let's break this into 2 collisions. I'm going to write for collision 1 to 2. I'm going to say that the initial velocity of 1 is simply called VO. And we can say that the initial velocity of object 2 is 0 meters per second. That's referring to this guy right here. Oh, and you know what? Before I go any further, let me just pause for a second here. The one thing that I'll write this in black so it stands out a little more. The one thing we're just gonna have to wrap our minds around is the fact that since we have two collisions, then the velocity of object 2 right here is going to have two different names. Because in collision 1, it's initially at rest, and we are going to be trying to find the final velocity of 2. And then in collision 2, 3 over here, we're basically going to be saying that this velocity it has after colliding with this first cart is going to be the same thing as what we would call the initial velocity of 2 for that second collision. You see what I'm saying here? The final velocity after the first collision is the same thing as the initial velocity going into the next one. Okay, it's all one velocity, but since we're breaking it into two parts, we're calling it two different things. If it clarifies it all, I can say the final velocity of 2 for collision 1. There's a little Roman numeral right there, and that's the same thing as the initial velocity of cart 2 for collision 2, and there's a little Roman numeral 2 right there. So hopefully that doesn't muddy the waters or anything, but that's going to be our assumption. Okay, so let's go about finding the final velocity of cart 1 and cart 2 for collision 1 and 2 right here. Okay, well, going back to our equations, and we can use the shorter versions, we can say that the initial velocity, the final velocity of object 1 is going to be m1 minus m2 over m1 plus m2 all times the initial velocity of 1. I'm going to go with small brackets right now. Okay. And we can write that the final velocity of 2, using our other short equation, is going to be 2 times m1 over m1 plus m2. Put a divide sign there. All that also times the initial velocity of 1 as well. So now let's simply plug in and find out what these final velocities are. So the mass of m1, what's that? Well, that's 4m. 4m minus mass of 2, that's 2m, divided by 4m plus 2m, all that times vi. I'm sorry, v, we said it was VO, right? VO. Well, we can simplify this, and instead of working downwards, I'm going to work sideways right here, but it shouldn't take very long to simplify this. 4m minus 2m. Okay, well, that's going to simplify to simply 2m. 4 of anything minus 2 of anything is 2 of that anything. 2m over 4m plus 2m, 2m over 6m. Times VO is what we have. Looks like V6. It's a VO. You can see now that our M's are certainly going to cancel out and become 1. And 2 6 simplifies to 1/3. 1/3 VO. Or you could simply say 0.33 VO. So what we're saying is that the final velocity after cart 1 collides with cart 2 is going to be 1/3 of what it originally was. Okay. So this is the final velocity of cart 1 after colliding with cart 2. Let's find cart 2's final velocity. That's going to be 2 times, what's the mass of m1? 4m, right? 2 times 4m over m1 plus m2. It's 4m plus 2m. All that times VO. We've substituted that in for our initial velocity of 1 right there, okay? Well, let's simplify this. We can do that. 2 times 4m, that would be 8m divided by 4m 2 plus 2m. It looks like 6m, right? Times VO. And we see our m's go away. They're going to cancel out and become 1. And that's going to simplify to 4/3 VO. Or you could say 1.33 VO. That's the fraction version of 4/3. Okay, so we have our final velocities for 1 and for 2. Well, that's only for collision 1 and 2, though. Let's see. Do I want to get a blank? You know, I'm going to write these probably up top, I think. I'm going to keep these all on the same slide right here. Let's take, you know what I'm going to do? I'm going to shrink these down a little bit so we have a little more space. Okay, sorry about that. I'm shrinking it down. You're like, what's going on? I'm just creating more space here. That's all. Okay, so now let's find the final velocities after collision 2. Let's erase that little guy. That's the top of the M, looks like it was. I'm going to write it up top here. No, you know I won't. I'll write it down at the bottom. I should be able to squeeze it in. For collision I need to make some more space for myself. I don't really have to, but I just want to because I want to make this neater. Goodness.